Okay, today we are going to be drawing Lewis dot structures. So this is the title of your page today, Lewis dot structures. So far, we've learned about electron configuration and Bohr models, and so today we're going to bring some of that back to kind of help us repackage it into something that feels new but is based in things we already know. Okay, and the reason for this is because we will be using Lewis dot structures for the rest of the school year because they are really useful. So what we're focusing on here is primarily electrons. So let's start off with reviewing something we already know. So let's take a look at the element oxygen. And we are going to write a, what's it called? Electron configuration, excuse me. We're going to write an electron configuration for oxygen. So if I'm looking at oxygen here on my periodic table, it's right here. So I have 8 electrons that need homes. So if I write this electron configuration, can you tell me what it would be? 1s2, 2s2, 2p4. So this is something that we had learned before with our electron configuration. Now we're going to take this electron configuration and turn it into a Bohr model. Do you remember when we went over Bohr models? So what's in the very center? Good, our nucleus, so our 8p plus, because that tells us that we have 8 protons, and the p plus is the indication that we have that. And how many rings are you going to draw? 2. So we're drawing 2 rings to represent those 2 energy levels that oxygen has. Okay. So far, this is just review, yeah? How many go on the first ring? 2, 1, 2. Now I want you to switch to the red pen. I love the sound, it's so fun. Okay, now how many go on the outermost ring?
6.
How'd you get 6? Good, so 2s2, 2p4, that's on the same energy level. And 2 plus 4 is 6. So on the outermost energy level, I'm going to draw 6 electrons in red. 1, 2, 3, 4, 5, 6. So this is all review so far. Okay, we did this in the last unit. But now we're going to kind of repackage this and put a pretty bow on it called a Lewis dot structure. But first, let's get a definition out of the way. These electrons on the outermost energy level, they have a special name, okay? These are called valence electrons. So these are called valence electrons. And valence electrons are your outermost electrons. And the reason why we care about these is because these ones are the primary electrons that are involved in bonding. So when we talk more about ionic bonding and covalent bonding, these are the ones that we're really going to focus on because these are the ones that are directly involved in that. Okay, flip back to the black color. Well, if the outside ones have a name, the inside ones need a name also. So we call the electrons on the inside, meaning everything that's not on that outermost energy level, we call them core electrons. And these are electrons on inner rings. And really we know that those rings are representing energy levels. So these core electrons are any electrons that are not on that outermost ring or energy level, okay? And really remember, it's not a ring, but it is a useful model to use. Okay, so this has all been reviewed so far. So now we're going to take this concept here and we're going to kind of simplify it to give us a shortcut, because we don't want to be writing electron configurations and drawing Bohr models every time in order to figure out valence electrons. We need a shorthand, and we use the shorthand when we're talking about bonding specifically. So we are going to now draw a Lewis dot structure for oxygen. Okay. So what I'm going to do is draw the symbol. So I'm going to do a capital O, and I'm going to make it big so that way it kind of stands out on my page. So capital O is the one-letter symbol. It's a chemical symbol for oxygen. I'm going to switch back to red because I'm going to represent all of my valence electrons today in my red pen. And how many did we say that it has? 6. So I'm going to now draw those 6 valence electrons around oxygen, okay? And just like we did the orbital drawings, how we had arrows up and arrows down and we paired them up, it's the same idea here about pairing them up. So I'm going to start at the top and just draw 1. And then I'm going to go to the right and draw another one. Bottom and left. Okay, right now I've got 4 dots that are representing 4 electrons, but didn't we say there were 6 valence electrons for oxygen? So I have 2 more. So just like the orbital diagrams, I have to pair them up. So at the top, I'm going to pair it up. And on the right hand side, I'm going to pair it up. Notice where I put the dots. I put them so that they're kind of like hugging the symbol. You want them hugging the symbol, because if you draw it out to the side going this direction, then that's indicating a chemical bond, like a single, double, or triple bond, and we're not there yet. We're just looking at Lewis dot structures of individual elements when they're neutral, okay? So you want to have it hug the symbol. Ta-da! You just drew a Lewis dot structure of an element. Is it really new? Not really. You know about electrons, you know about valence electrons, you know about Bohr models, electron configurations, chemical symbols. We're kind of just repackaging it and putting a bow on it, and we're only representing those valence electrons. So instead of drawing all of the Bohr model, we're just looking at that outside energy level, okay? One thing I do want to point out is if I look on the periodic table, we know that there tends to be lots of patterns on the periodic table, right? That's the whole point of it. So if I look at oxygen, what A group is oxygen in? 6A. And how many valence electrons did we draw? In my black pen, so switch back to black pen, I'm going to write group 6A. And I'm going to put that there to see if that comes back. Does that become important? Okay. All right, let's do another one and see what happens. Let's go ahead and do arsenic. So now we're going to do the same thing. We're going to write an electron configuration and draw a Bohr model for arsenic, and then take that and turn it into a Lewis dot structure. So arsenic is right here, number 33. So if I'm thinking about electron configuration, where does arsenic end? 1, 2, 3, 4, P3. So I'm ending my electron configuration at 4p3, which means everything before it is full. So if I'm writing my electron configuration then for arsenic, what am I going to write? Good. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What comes after 4s? Perfect. 3d10, 4p3. Okay, so that's our long electron configuration for arsenic. So now let's go ahead and write and draw a Bohr model. So what's in the middle of it? Good, our number of protons, and since this is element number 33, we have 33 P plus, because I have 33 protons. I don't have a mass number, so I don't know the number of neutrons, so we're just putting 33 protons. And how many rings am I going to draw? 4, because we have 1, 2, 3, 4 energy levels. So here we go. 1, and my circles are not great. 1, 2, 3, 4. Okay. Sorry, my circles are not perfect, but there they are. And remember, the Bohr model is not completely accurate, but it is a useful model. All right, so now let's go ahead and start putting electrons on the rings. So on the first innermost ring, how many electrons go there? 2, 1s, 2. You will see some representations of Bohr models where they're paired up. Either way. 2s2, 2p6. How many is going to go on the second? 8. 2 plus 6 is 8. 1, 2, 3, 4, 5, 6, 7, 8. How many go on that third energy level? Good. 3s2, 3p6, and 3d10. So 10 plus 6 plus 2 is 18. So on that third energy level, I'm going to draw 18 dots that represent 18 electrons on the third energy level. 1, 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, now I'm on that outermost energy level, so I'm going to switch to red because we're representing valence electrons today with our red pen. How many go on the fourth energy level? How'd you get 5? Perfect. 4s2 and 4p3. Those are the fourth energy levels, so 2 plus 3 is 5. So on this outermost energy level, I'm going to draw 5 electrons to represent my 5 valence electrons. And I'm going to label it one more time just so it kind of sinks in my brain that we call those ones on the outermost energy level valence electrons. So the electrons in the first, second, and third energy levels, those are all called core electrons because they're on the inside. The ones on the outside are called valence electrons. Our Lewis dot structure represents only valence electrons. So using our black pen, let's go ahead and draw a Lewis dot structure. For arsenic. To just show valence electrons. And the reason why we care about the valence electrons specifically is because when we get to ionic and covalent bonding, it is what determines how it bonds. So arsenic is capital A, lowercase s. And I'm going to use my red pen for my valence electrons. How many valence electrons does it have? 5. So I'm going to draw 5 dots starting at the top, going in a circle. 1, 2, 3, 4. Now what? Pair it up at the top. Ta-da! This is the valence electrons showcased in a Lewis dot structure for arsenic. Isn't this way simpler than trying to draw a Bohr model every time? Because when we're talking about bonding, what we're interested in is how the valence electrons are behaving. Because the core ones typically don't change. When we get to the d orbital and we talk about transition metals, some interesting things happen in terms of what happens in bonding because of that d orbital. And we'll talk more about that when we get there in the next unit. Okay, so just to stay with my pattern here, I said oxygen was in group 6A. So arsenic, right here, is in group what? And how many valence electrons do we have? Okay, so there is a pattern here. And this works with our A representative elements, okay? And the reason why this works is because of electron configuration. If I'm in group 1A, these all have an S1 orbital, meaning it has an S orbital with a 1 electron in it as its outermost energy level. So 1A has 1 valence electron. Group 2A, these all have an S2 as its outermost energy level. So that's 2 valence electrons because of S2. Well, if I jump over to 3A, and again, we're just staying with the tall columns, meaning our representative elements, these all have an S2 and a P1. Well, 2 plus 1 is 3. So group 3A all have 3 valence electrons because of its electron configuration as its outermost energy level. Group 4A, you see where we're going with this? Has 4 valence electrons because it has 2 from 2s, or from the S2, and then it has 2 from P2. And no matter what energy level it's in, it's always the same because it's the same pattern. Group 5A then has how many valence electrons? And group 6A then has how many valence electrons? So the group number of our representative elements, the A group, tells us how many electrons there are in that outermost energy level. So when we're drawing loose dot structures, instead of writing out an electron configuration and drawing a Bohr model, we can look at the group number. But the reason why that shortcut works is because of electron configuration, okay? Okay, so therefore, let's go ahead and write it on our notes page here as a shortcut, a reminder of our shortcut. Therefore, the group number, and remember, we're talking about the A group, meaning our representative elements, is the number of valence electrons and comes from, and the reason why it works, that's what we're saying, comes from the electron configuration shows that outermost shell or energy level. Okay, so our A group, that number tells us the number of valence electrons for that element when it's neutral, and it comes from the electron configuration of that outermost shell. That's why this pattern works. That's why the trick works. Instead of just memorizing the trick, that's explaining where we get it from.
Where does it come from? The electron configuration shows
Oh, sorry, it probably doesn't read very well. It comes from the electron configurations. Here, let's do this. Outermost shell. Let's do that. Comes from the electron, that makes more sense. Sorry about that. Electron configurations, outer, I don't even need the word the, huh? Okay, electron configurations, outermost energy level. Sorry about that. Okay, so I'm going to underline the electron configurations, outermost energy level in red, because that is what we've been seeing with our valence electrons. And then I'm going to underline group number, meaning the A group is the number of valence electrons in blue, because we showed 2 examples in group 5A and group 6A. So the reason why I'm underlining these is really just to connect it in our brains of where we're getting this kind of trick from. Okay. So let's write out some steps, some how-to steps. So how to draw Lewis dot structures. Number 1. Write the chemical symbol, meaning that 1 or 2 letter symbol from the periodic table, and remember only the first one is capitalized. Number 2, the number of dots we draw is or equals the number of valence electrons which comes from the group A number, meaning 1A, 2A, 3A, 4A, or you can get it from the electron configuration. I do want to pause here though and talk about helium. So for our class, there is an exception in helium. So we're going to pause real quick. If I look at helium, helium is in what? Group what? 8A. So according to our pattern, that would tell us that it has 8 valence electrons. But that's not possible, because how many electrons does it have? 2. So the reason why helium is over here, considered a noble gas, is because that 1s orbital is full. It's 1s2. It's full, just like all of these other noble gases have full outermost electron shells. So it fits the pattern, okay? But helium is 1s2. So if I draw the Lewis dot structure of helium, I am not drawing 8 dots. It only has 2 electrons. But those 2 electrons are paired up. They are full at 1s2. So on my helium Lewis dot structure, this is the exception that you would draw those 2 electrons as paired up, straight out the gate. That's what it is. You would draw it as paired up because it only has that 1s orbital, and that 1s orbital is full. So that is our exception that we have for this class, is in helium.
Usually you look for like the red dots everywhere, right?
Right, I did the color coding, the red dots, to kind of stick in our brain that those are our valence electrons, and those are the ones we care about in Lewis dot structures. Okay, so that's our exception there for helium. So let's keep with our list then. Draw the dots clockwise, meaning our electrons. Starting at the top, one at a time. And lastly, number 4, if necessary, continue placing dots representing our electrons in pairs.
Oh,
17. So, like, which one are you looking at? Chlorine?
yeah, or something like
Okay, well, it's in group 7A. So how many valence electrons does it have? 7. So we're only drawing 7 dots. So you're only interested in drawing the valence electrons in Lewis dot structures. If we want to see all of them, we'll draw a Bohr model. So if I want to see all of the electrons on all of the energy levels, I'll draw a Bohr model. But if I only want to see valence electrons, I'm going to draw a Lewis dot structure. So with that, let's just do chlorine as an example. So down here, let's do chlorine. So Cl. Chlorine has 7 valence electrons. So I draw 7 dots starting at the top, going in circles. 1, 2, 3, 4. Are we done? No, we have to start pairing them up. 5. Okay, now this is important. Where you put the dot matters. You want it to hug the symbol, because if I put a dot out here like that, this indicates if I go this direction or vertical or anything that's not hugging the symbol, it indicates a chemical bond, like a single, double, or triple bond, and that's not what we're drawing yet. So you do not want to place the dots going out from the symbol. You want them to hug the symbol. It's like the electrons are hugging the symbol. So this, how I've drawn it for chlorine, would be correct. You do not want to draw it heading out from the symbol. Another one to point out is, let's draw boron. Boron is in group 3A. So how many valence electrons does it have? 3. Okay, so when we were drawing orbital diagrams, we would draw the S, 1 up, 1 down, P, 1 up. Yes? Well, when we draw Lewis dot structures, we separate them out. So I would say 1, 2, 3. And I would not pair these two up. And the reason for that is something called orbital hybridization, where the S and the P orbitals kind of smash together. And when we get to covalent bonding, we'll talk about that a lot. But for here, we're going to separate them out and we're going to pair them up only when we need to. Okay, so this is how we are drawing Lewis dot structures using the periodic table.